Hi and welcome everyone. In this video, I want to talk about the power series, and later on, we're going to see how power series is used in different applications and how we can use power series to solve differential equations. So now let's go over the definition of a power series. Uh, a power series is a series of the form you have the sum of n starting from 0 to infinity c sub n x to the power of n. If I expand this and substitute, if you put 0, you get c of 0 and x to the power of 0 is just 1 c1 times x, c2 times x squared, c3 times x cubed, and it keeps going. And cn's are called the coefficients. Some notes here to notice: a power series can be tested for convergence or divergence. So a power series may converge for some values of x and may diverge for other values of x. The sum of series is a function, so we can write that as a function. F of x equals to c0 plus c1x plus c2x squared and up to cn x to the power of n, or we can keep going. Now the domain of f of x is the set of all x for which the series converges. So, and be patient, we're going to see all this. F of x is a polynomial, so if you look at f of x, that's a polynomial, and polynomials are nice function, and that f of x has infinitely many terms. An example of that: if you have the sum of n starting from 0 to infinity, x to the power of n, you know, if you put 0, you get 1 plus x squared plus x, and it just keeps going. And if you notice that this is a geometric series, the first term a is 1, and then each time you multiply by x. 1 times x is x, 1 times x times x is x squared, and it just keeps going. Now, we know that a geometric series converges when the absolute value of the ratio, and here ratio is r, is less than 1. Since here the ratio is x, so this series is going to converge for absolute value of x less than 1. And what happens, it converges to a sum, and that sum is given by a, the first term, over 1 minus r. So please review the geometric series and the sequences from pre-calculus. So we can write this as the sum n starting from 0 to infinity x to the power of n as 1, which is the first term, over 1 minus x, and that's the ratio. So the power series representation of 1 minus x is sum of n starting from 0 to infinity x to the power of n. This function can be written as that, and that's a polynomial. It converges when the domain is when absolute value of x is less than 1. Now let's see what happens. If x equals to, I picked a number between -1 and 1. X is 1/2. If we expand this, we get 1/2. 1 plus 1/2 plus 1 over 4, and just keeps going. Those numbers get smaller and smaller. So that's a finite sum. And that's approximately 1 over 1 minus, we can use that, 1/2, and you get 2. So this converges to 2. If, on the other hand, if I take x equals to 2, then if I expand the series, I get 1 plus 2 plus 4 plus 8 plus 16, and they get larger and larger, so it goes to infinity, so that's divergent. Now let's generalize this. A power series can be written as, so if you see this notation, sum of x starting from 0 to infinity c sub n x minus a to the power of n. If you expand that, you get c0 plus c1 times x minus 1 plus c2 times x minus 1 squared, and so on. So the way you call that, you say this is a power series in x minus a, or power series centered at a. So you can hear that term also, analytic at x equals to a. Power series, or you can hear power series about a, so they all mean the same thing. So, and analytic algorithm is it converges for sure at x equals to a. Let's look at this example. So we have a power series here, and the question is for which values of x is this power series is convergent. When you have a power series, most of the time you use the ratio rule, the ratio test, and the root test also it's used, but most of the time you use the ratio test. Let's do that for this one, see what you get. What is the ratio test? You have to take the limit as n approaches to infinity of a sub n plus 1 divided by a sub n. So if you substitute n plus 1 by n, you get n plus 1 factorial divided by n factorial times x to the power of n plus 1 divided by x to the power of n. I can be right n plus 1 factorial. That's just n plus 1 times n factorial. Why do we do that? Because we know we can cancel those. And how can we write x to the power of n plus 1? That can be written as x times x to the power of n divided by, that's divided by xn. Why did we do that? Because we know they are going to cancel each other. And at the end, you're left with absolute limit as n approaches to infinity, absolute value of n plus 1 times x. Now, n plus 1 is always positive, so you can say this is limit as n approaches to infinity of n plus 1 times absolute value of x. And if you put infinity for n, you get infinity. This series only converges at x equals to 0. Why is that? I just put the ratio test here. For ratio test, if you take the limit as n approaches to infinity of absolute value of n plus 1 divided by a sub n, that number is less than 1, then the series is convergent. If that number is greater than 1, then it's divergent. And then when you get that number to be 1, then it's inconclusive. So that's why if x equals to 0, then this becomes less than 1, and it's going to be converged only at x equals to 0. Now the series, we saw this one, but let's do the same thing, see what happens. If we do the ratio test for that series, again, the ratio test is limit as n approaches to infinity of a sub n plus 1 divided by a sub n. Substitute x to the power of n plus 1 divided by x to the power of n, and that's just x times x to the power of n divided by x to the power of n, and x to the power of n's cancel, and you're left with absolute value of x. In order for this to cancel, then absolute value of x from the ratio test again, right here, has to be less than 0. That means x is between -1 and 1, so it's going to converge. If absolute value of x is greater than 0, that means x is greater than 1, or x is less than or equal to -1, then it diverges. However, here I put red lines because we don't know what happens at the end of the endpoints of the interval. So we have to test it. If you substitute x equals to 1, you get 1 to the power of n, and that's 1 plus 1 plus 1 to infinity, so it diverges. And if you put -1, then you know you're going to get an alternating series limit as n approaches to infinity of an alternating series. That -1 to the power of n does not exist, so it's going to be, this is basically divergent. So now, what is the conclusion? Here we have absolute value of x. If I draw this number line, absolute value of x less than 1, that means between -1 and 1, the series is convergent. We call that the interval of convergence. After 1 and before -1 is divergent, and is also divergent out of -1 and 1. Now, when we write absolute value of x less than 1, this one here is called the radius of convergence, and we put r, the symbol is r. So general, if we have a power series like this, there are three possibilities. So it might converge only at x equals to a, just like we saw in the example. It can converge for all values of x. That can happen also. So you just get a limit and that's less than 1. Or converges when absolute value of x minus a is less than r, the radius of converges, and diverges when absolute value of x minus a is greater than r. We saw the examples here, that's just a summary. And when x equals to a plus or minus r, these are the endpoints of the interval. It can be convergent or divergent. So then you need to check, substitute those values for x and check that. Now, what is our goal? Our goal is to represent functions as power series, because when you do that and you get polynomials, then they're very easy to deal with. And also, you're going to see some differential equations are solved by using power series. So let's go over that. Representations of functions as power series. One simple one and the most obvious one, we saw that 1 over 1 minus x can be written like 1 plus x squared plus x cubed, and sum of n starting from 0 to infinity x to the power of n. Radius of convergence is 1. Now, if I have this function, I want to represent that as a power series. So I can go to this one. First of all, 1 over 1 plus x squared, you write that 1 over 1 minus, because you have to have that negative sign. And again, this is the ratio now. So you can just substitute. Instead of x, you put negative x to the power of 2 and to the power of n. But this is like negative 1 to the power of n. So you can take negative 1 to the power of n out times x to the power of n. Again, when you have that, that means it's going to alternate. If you want to find the interval of convergence, you do the same thing. So you know that now that needs to be less than 1. So absolute value of that means x squared less than 1, and same thing, absolute value of x is less than 1. So it converges between negative 1 and 1. And of course, it's going to diverge when x is greater than 1 or x is less than 1, and at negative 1 and 1 is going to diverge also. Now, if you have a power series, you can differentiate or you can integrate. So if you have this power series, now the radius of convergence is r. So, and we say, therefore, it's going to be differentiable and continuous this interval. So how do you find the derivative? Just simple power rule. So it's C1, because the derivative of this constant is 0, and it's 2 times C2 times x minus 1, and that's 3 times C3x minus a, not 1a squared. So the general term, you can write this as, this is just the power rule of differentiation, n times c n x minus a to the power of n minus 1. The integral of that, so you know the integral needs a constant first of all, and you just take the integral term by term. So it's c0 x minus a, and that's c1 x minus a squared divided by 2, and so on, c2x minus a cubed divided by 3. And the general form, you can write that as the term, or general term is c plus sum of cn times x minus a to the power of n plus 1 divided by n plus 1. And this is the power rule for integration. Or another way of showing that, the derivative of this power series, you can just take that inside is the derivative of that expression. So, and the integral of the power series, you can take the sum out is the integral of that expression. Now let's talk about Taylor and Mclaren series and see how they come up to write any function as a power series. If we have this power series, we saw you're not familiar with this notation, radius of convergence is r. Let's calculate f of a. F of a is gonna make all these 0. We're just left with c0. Now if we take the derivative, then we get c1 plus the derivative of c0 is 0. It's a constant, plus 2c2 times x minus 1 plus 3c3x minus not 1 but a again squared and so on. If f prime of a is going to make all these 0, you're left with c1. F double prime of x is 2c2, and here 3 times 2, I just wrote it, 3 times 2 times c3x minus 1, 4 times 3 times c4x minus not 1, a again, x minus a squared plus, and it just keeps going. If you calculate the second derivative, f double prime of a, these are zeros, so you're left with 2c2. We're getting to a conclusion here. The third derivative, again, you'll see what happens, 3 times 2 times c3, and here you get 4 times 3 times 2, and I wrote it like that, times c4 times x minus 1, and it continues. What's the conclusion? F triple prime of a is 3 times 2 times 1 times c3, and that's 3 factorial. The fourth derivative, if you put a in there, you kind of see it's 4 times 3 times 2, so that's 4 factorial. So the general term, the nth derivative, if you calculate a, substitute in the nth derivative, you get n factorial times cn, and if you isolate c sub n, you get the nth derivative of a divided by n factorial. So that's how we can get the coefficients, by taking the derivatives. Now, what is the conclusion? If you have a power series like that, then this cn can be substituted by the nth derivative of a divided by n factorial. So you can write f of x as f of a plus f prime of a divided by 1 factorial times x minus a, f double prime of a divided by 2 factorial x minus a squared, and so on. So that means that we can write any function as a power series and as a polynomial. Now this, the general term is written like that, the nth derivative of a times x minus a to the power of n divided by n factorial. This is called the Taylor series of the function. There is a special case when you can say a equals to 0, and you just get, so f nth derivative of 0, because a is 0 times, if this is 0, you get x to the power of n divided by n factorial, and that's the most common one. And you get f of 0 plus f prime of 0 divided by 1 factorial, f double prime of 0 divided by 2 factorial, and so on. And let's not forget the x's here. So we have x, and here we have x squared. So, and this is the most common way. Now, we'll see how we can use this in to solve differential equations. And I think after this lecture, this is a good review of calculus too, so you can remember and use them to solve the differential equations problem. Thank you for watching, and I'll see you in my next video.